Alright, so in the last video we learned how to use variation of parameters to solve non-homogeneous second-order differential equations with non-constant coefficients. And in this video I want to show you how you can still use it for an equation that actually doesn't have an explicit solution like we did in the last problem. So the idea is we express our differential equation in the form y double prime plus ax, y prime plus bx, y equals to c of x, and in this case we already have the differential equation in this form, so we don't need to do that step. Now the second step is to find the homogeneous solution, so set this function equal to 0 and solve for the equation y double prime plus 4y. So this is a second order homogeneous with constant coefficients, so we can use the general solutions we know of. So we find a characteristic equation, and then the roots are going to be r, so let's write this down, r minus I2, r plus I2 equals 0. So we have complex roots, so r1 and 2 is going to be equal to plus or minus I2. Now we know that for complex roots the general solution should look like c1 times cosine of the imaginary part, so 2t, plus c2 of sine 2t. So basically this is going to be our y1, and this part here is going to be our y2. So we ignore the constants for calculating the Wronskian, so let's do it with respect to these two. The Wronskian of these particular solutions is going to be the determinant. So here we have cosine of 2t, here we have sine of 2t, and now we differentiate this and put them in the second row, so the derivative of this is going to be minus 2 sine of 2t, and the derivative of this is 2 cosine of 2t. And now what we do is we cross multiply and then subtract, so this becomes 2 cosine squared of 2t, and then we have minus, so that becomes a plus 2 sine squared 2t, and by trigonometric identities we know that this just simplifies to 2. So once again we got a constant, which is a really nice result because we know that the Wronskian is the denominator of the ratio that we integrate to find the other functions. Okay, so now we're going to proceed to find the solution to the non-homogeneous equation. So we know that we're going to have some function v1 of t equals to the integral. So this one is a negative, so it's going to be minus the integral from 0 to t of the function y2s times cs over the Wronskian evaluated at s ds. Alright, so let's see what we get in this case, because I feel like this is actually going to come out to be a surprise to you. We're going to get minus integral from 0 to t, and I'm not going to make the same mistake I did in the last video where I put y1 here, what I should have put y2. So y2 we know is sine 2t, so this is what goes in here, sine 2s, because remember we're replacing the t by s just for the purpose of representing the integral in a more comprehensible way. And then cs, well, let's go back up and see what it is. Well, c of t is natural log of t plus 1, so c of s has to be natural log of s plus 1 ds, and the Wronskian we know is just 2, so in the end we can write this as minus half from 0 to t sine 2s times the natural log of s plus 1 ds. Now this is an interesting expression because how do we actually go about integrating this? You might think, oh, maybe we can use integration by parts or something like that, but there is no exact form of this integral. So what I'm going to do is actually just leave it as it is. And you might find that a bit weird because if we're trying to find a solution, it seems pointless to have a solution in terms of an integral equation. But you'll see that this is a much more useful thing to have than just have the differential equation in its original form. So now I'm going to find v2. So this is going to be equal to integral from 0 to t of y1s cs over Wronskian s ds. And this is going to be 1 over 2. So I'm going to extract the Wronskian. We know that's 2. Integral from 0 to t. Now y1 is cosine of 2t. So this is cosine 2s times natural log of s plus 1 times ds. And once again, we have an expression here. We have an integral that cannot be solved exactly. So the best thing we can do is to leave it as it is. Okay, so we know that the general solution to this problem is just going to be a combination of the homogeneous solution, so yh plus yp, which is the non-homogeneous solution. And we know that the non-homogeneous solution is v1 times y1 plus v2 times y2. So if we put these two things together, we're going to get the following. So yh, we found that was c1 times cosine of 2t plus c2 sine 2t. And I'll see if I can fit all of this in one line because it's going to be a really long equation. So v1 times y1, well, y1 is a lot simpler, so it's just cosine 2t. So I'm going to put that outside, but we have this minus here. So let's say minus half. y1 is going to be equal to cosine of 2t. And v1, which we found here, is going to be this integral. So that's going to be the following. So hopefully, I don't think it's going to fit anyway. 0 to t of sine 2s times natural log of s plus 1 times ds. And now v2 times y2. So y2 we know is sine 2t. So this is going to be plus half of sine 2t times the integral from 0 to t. So this is v2. Is going to be the following. We have cosine of 2s times ln s plus 1 ds. And this would be the general solution to our problem here. So you might say, well, this is just an integral equation. We don't have an explicit solution for y of t. So how is this more helpful than having the differential equation and solving it numerically? Well, the difference is that you know you can use numerical integrations such as Simpson's rule or trapezoidal rule or some kind of numerical integration technique to find the value of this integral and this integral, and you know that you can control the accuracy of that with that very easily. This is much more stable than trying to solve the original differential equation numerically. So basically what this is that if you grab something like y of 1, what you're going to do is you just put 1 into every t. So this is going to become 2 times 1, 2 times 1. And here you're going to evaluate an integral from 0 to 1 of this thing. So you use a numerical integration technique. And to find the solution over a whole range of t, all you do is for each value of t, you will evaluate these integrals. So you will actually find out that this is actually still a closed form solution. It is implicit because we have this integral kind of terms here, but it is still much more useful than trying to solve the differential equation numerically from scratch. So variation of parameters is a really general method, and you will find that it's actually really useful for finding expressions like this as well. So it can actually be used in most cases, and I highly recommend variation of parameters for dealing with complicated differential equations like this one.